Anyways, enough stories. How's lab 1 going? Any obscure problems? No obscure problems? It's all working? For amusement's sake, I'm not going to talk about this particularly right now, but for amusement's sake, you might want to go look at the CTMU, the Charge Time Measurement Unit. It's designed for measuring resistances and capacitances. I'll leave it at that. What we really need to start on today is Lab 2, because the Tuesday night lab has to start on Lab 2 1 week from today. You start on Lab 2 the day after you finish Lab 1, otherwise it is not a 2-week lab. So there's no downtime. As soon as you finish, you start the next lab. So we need to talk about this so that you can do the homework. And what I'm going to ask you to do for Lab 2 is to generate is to build a DTMF generator, dual tone multi-frequency generator, and make it compatible with international telephony standards, but also add speech feedback so that when you press the 1 button on the simulated phone, the system is going to say 1 and so on. So there's going to be several things we need to talk about before next week or so. The first is how to interface a keypad so that you can have a dialer input. And that really has 2 pieces, scan and debounce. You have to figure out how to scan this set of switches, but you also have to debounce it. Debouncing you have to have because I think if any of you held a button down on or pushed a button on your cell phone and it pushed the one on your cell phone and you got 3 ones in a row, you would throw the cell phone away. So you have to match the speed of the hardware to the speed of the human, and that means debouncing the keypad. We have to talk about how to connect a DAC to the whole system so that you can get an analog signal out, high quality analog signal out to meet the telephony standards. We need to talk about direct digital synthesis, which is a mathematical scheme for generating sine waves. So there's a bunch of stuff to go over. But just for orientation, you're going to build a device with a keypad. It'll probably look something like the image towards the bottom of the keypad page. You'll have a 12-key keypad. You'll have some sort of display over here. I was using the same test code with one more thread to make sure that the keypad didn't interfere with the display, with the TFT display. And hooked to this is going to be a speaker. Now we have amplified speakers. The output from the DAC is a 1-volt signal, more or less, 1-volt peak signal. And it's low power. So you're going to have to amplify it. We have amplified speakers, which are to say speakers that have a green plug on the end like you'd hook into the line out of your computer. And you're going to hook those up to your circuit and then use those. If you use earphones from your phone, you can probably hear it also. And that might be kind for you to do, because after listening to poorly formed touch tone sounds for 2 weeks, the TAs start to foam at the mouth. They get a little crazy. But that's okay. if you want to beep them senseless. So overall, what you're going to do is you're going to press the keypad, store up to 12 digits, and then when you press dial, it should play out the touch tone sequence as if it were dialing a phone, meeting the touch tone standards as outlined in lab in homework 1, homework 2. It's going to produce the words representing the digits when you press the buttons directly. And of course has to do this without audio glitches or without being reset. Oh yes, and when you press a button, you press the star button, it's going to erase the entire stored number. When the pound button is pressed, the DTMF signal for each digit is produced for at least 65 milliseconds. The tone bursts have to ramp up, so the tone bursts are going to look like this rather than this. So you have to amplitude modulate the sine wave so that you avoid the corners here, because whenever you have a corner in a signal, you have broadband signal. And the way you'll hear this is for a short burst, like a 60 millisecond burst. If you have sharp corners at the beginning and the end, you will hear that as if there was a high energy square wave playing. In other words, it will click. And it's very annoying. Frequencies are given here. This is a table of the standard DTMF frequencies. There's always 2 frequencies played. And why is that? That's so your voice doesn't trigger the system, because in the bad old days of analog telephone, the touch tone signals went over the same signal channel as the voice. And so if you could whistle 2 frequencies at the same time, you could dial the phone. Now, the frequencies that are chosen are not harmonically related, so they're fairly hard to whistle at the same time. So 697 and 1209 hertz played simultaneously represents dialing a 1. And you're going to need to be able to generate all of these frequencies within the specification given. I believe I put it in homework 1. Let me just check that. Homework 2. Yes, here's that. According to the DTMF spec, frequencies have to be within 1.5% of nominal. So it'll be interesting to find out how accurate the internal resonator is in your system, because that'll determine the timing accuracy and therefore the frequency. All spurious frequencies must be 20 dBs from the main tones. Duration of any individual DTMF tone shall not be less than 65 milliseconds. Time measured from 90% of its steady state to 90% of it, drop to 90% of its steady state. The pause shall not be less than 65 milliseconds, and that's measured at the 10% level. You could just push these out to 70 milliseconds. It says these are minima. Push it out a little bit, the timing becomes less critical. You don't have to calculate 90% times. But that is what you're going to be generating based on a series of key presses. Any questions? Yeah.
Question 1, is the DDS sampling only done on the dual tone, or is it done for the numbers?
So the direct digital synthesis will generate the sine waves, And then there are two different schemes I listed, which are not the only schemes for generating a voice signal. One of the voice schemes, which gives good compression, 8-to-1 compression, uses a weird spectral sampling that I hallucinated one day and implemented. I'll show you what it sounds like. So this is the voice sample, original voice sample.
1, 2, 3, 4, 5, 6, 7, 8, 9, 0.
Now here is, if we take 30 log-spaced frequency analyzer channels, so these are second order filters, logarithmically center frequency spaced across 340 hertz to 3400 hertz. We record the amplitude, average amplitude output of each one of these filters for 18 or 20 milliseconds. Pass the filter coefficients over to the PIC, and then reconstruct using only sine waves at the center frequency of the filters. So now we're going to play this back as if it has only 30 sine waves making it up. We get this.
1, 2, 3, 4, 5, 6, 7, 8, 9, 0.
It's kind of a weird effect. In fact, nobody quite knows. Did it seem understandable? Kinda. Nobody actually knows why this works. You can, if you're more optimal with the sine wave generation, you can drop it down to 3 sine waves, and it still works. But then you have to do what's called formant tracking. You have to track the loudest frequencies. I'm just doing all 30. So let's say how far down can we go? We can double the compression if we only use 15 filter channels.
1, 2, 3, 4, 5, 6, 7, 8, 9, 0.
And then we can go down even further to 8 channels.
1, 2, 3, 4, 5, 6, 7, 8, 9, 0.
And I doubt if you didn't know what those words were, you wouldn't be able to understand them at 8 frequency components. Log distributed across one order of magnitude in frequency. It's an interesting psychological effect. It's good compression. But to implement it on the PIC side requires 8, 15, or 30 DDS units, as you were saying. So in this case, you need a ton of direct digital synthesis units to implement the compression. Another way to do it, which only gives about 2-to-1 compression, is just dropping bits. This goes to the other end of the complexity spectrum. We're going to take 8-bit samples, 8-bit voice samples, truncate the last 4 bits, and just throw them away. So now we have 4-bit samples. We're going to pack into 8-bit cars for density. And this works for any WAV file, by the way, WAV file. Compress it so you can use your voice if you want to record your own voice. You compress it down to 4 bits and you play it back through the DAC. Yes?
So in the former question where it asked the sampling frequency, that's just referring to the dual tone range, not the FE.
So the sampling frequency required in the DTMF dialer is going to then inform what you have to do for the speech, because you're probably going to put everything into one interrupt service routine. So that if you come up with a required rate of 8 kilohertz for the DTMF dialer, you're going to want to use the same frequency for the voice. If you come up with 16 for the DTMF dialer, you're going to want to use 16 for the voice, so that you can put it all in one interrupt service routine.
So this is going to be like a blocking thing, right? So when it's generating speech, it won't respond to like button.
So the question is, what is the right protocol for when the human presses a button really fast? Should you play the rest of the speech from the first button, or should you interrupt the speech when you press the second button? And you can do either that you want to. It's not specified in this case, but you need to justify what you're going to do. It can be blocking, but it need not be. There's an example on, so the VREF generator, the voltage reference generator on the PIC32 is programmable at a very high rate, so it's a DAC. It's only a 4-bit DAC. That's one reason I tried to use 4-bit speech here to see what it sounded like. Let's listen to some 4-bit speech.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
So the effect of truncating bits is to spread impulse noise across a fairly wide spectrum. So it generally actually sounds better than the highly compressed spectral data for
0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
It sounds a little raspy and nasty. You could, there's probably enough memory on the PIC32 so that you could just use 8 kilosample per second, 8-bit voice data, which is considered toll grade. It's considered what you would expect to hear over an old-fashioned analog telephone. You could probably, which has a bandwidth, by the way, of about 3,400 hertz. So you could probably just take a wave file, quantize it to 8 bits, generate a gigantic C header file. Gigantic. Who cares? C compiler doesn't care. And so, for instance, here's a header file of the packed digits, and these are all 10 digits, and there's a lot of 102s at the beginning, which turns out to be silence. If you specify that you want these to be static, constant, oh, where to go? Where to go? There it is. If you want these to be static, constant types, then this gigantic array is automatically stored in flash for you rather than in RAM. Because you've got 128 kilobytes of flash, but you've only got 32 kilobytes of RAM. This won't fit in RAM, but it will fit in flash if you say that it's a constant array. So you can put a pretty big array, if you speak the numbers really fast, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, then first of all, you don't have to worry about interrupting the digit because you can't press fast enough. What? You can't press fast enough to have to worry about concurrency. Secondly, it takes less flash. So if you record your high voice, if you count at high speed, or find a synthesizer that'll do that, you can cut down the flash requirements. Maybe you can just avoid the compression altogether and get a really good sounding speech out. If you want to go crazy, you could implement adaptive differential pulse code modulation, which with a 4-bit signal will give you the same quality as uncompressed 8-bit speech. with a 2-bit signal, 4-to-1 compression, it'll give you reasonable quality even. Slightly crackly, but reasonable quality. So you're welcome to use this is the WAV file I used for this one.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
This happens to be a commercial voice synthesizer, and what I would say the reasonable way to do this would be to quantize, or to use the WAV file, or to compress the WAV file, as I talked about on the VREF page, and store one array with all the digits. And then you go to the MATLAB and you say, where are the quiet places? You get from MATLAB, you get the index number in the array of the quiet places, and now you know the boundaries of each digit, so you can play back one at a time by just indexing into the array at the appropriate spot. So you don't have to have 9 different arrays or 10 different arrays, or actually, yeah, 10 different arrays. You just have one array with a bunch of indices, but you could do it either way. You could store 10 small arrays also if you wanted. If you found it easier to say 1, and then trim that down with MATLAB until you just barely get the end of the word, and then 2, and trim that down until you barely have the plosive at the beginning, and maybe trim a little bit of the energy off the front, you could probably save a little bit of space. In fact, you could save space because, after all, I did have to stop speaking between each digit. But this is a design decision you get to make. There's a fairly easy path through this, but it may not be optimal. Any questions on the speech generation stuff? An interesting final project would be to try and implement linear predictive coding. Code-excited linear predictive coding, CLEP, C-L-E-P. It's the state-of-the-art for compression in speech. It's a hog for doing arithmetic. You have to do a lot of arithmetic to make it run. I think the PIC32 is fast enough, but I'm not sure. Do you have questions? Yes?
The second example, did you play band 16 kilohertz or 8 kilohertz?
Whatever it is on the VREF page, I believe it's 16.
It was alternating between the two things on the page.
When in doubt, look at the source. Anything else on speech?
Can I ask a question about Lab 1?
Sure.
Okay, so we had like a resistor that was in the hundreds of kilo ohms, and we attached it to 3.3 volts, and we measured like the floating side of the resistor, and it was not 3.3 volts. It was like, I think like 2 point something. Is there like an explanation for that?
How did you measure it?
Using a scope, I think.
And what's the input impedance of the scope?
I'm not sure.
Aha! 1 megohm.
Okay.
So if it's 100 k ohm, you're going to lose 10%.
Right.
You can flip the probe to 10 megs.
Okay.
What else? Okay, so next piece of this is we got to get the signal out. We're going to use a SPI DAC, serial peripheral interface DAC. It's a very nice DAC. It's another microchip part. It is mercifully easy to understand. We're using the 12-bit dual voltage output model, so you get a fairly high quality output And the interface is very easy. You got a power supply, you got ground, you got 2 voltage outputs. You can force them to be simultaneous load, but you don't need to, so you just wire this low and leave it low. This is the enable pin. And then there's 4 interface lines, 3 interface lines to the computer. There's a chip select, which says, you're the one I'm talking to. There's a clock for synchronous communication, and there's a data line. And every transaction is 16 bits. There's 4 command bits and 12 data bits. It's binary offset. There are no negative numbers. So 0 code is 0 volts. Code FFF is 2.047 volts. Mapped just exactly like you'd expect. A millivolt per code. Very nice, very easy to use. Internal references, just works. So what you're going to do is through the serial interface, you're going to feed it 2 signals. You're going to feed it 1 channel of DTMF data and 1 channel of voice data.
Just a quick question. In the sample code, when we are talking to the DAC, why are we converting to the fixed 16 format and do all the calculations?
So fix 16 is a detail that I'll talk about, but what I was using in this code was I was probably doing some filtering. And whenever I want to do filtering, I switch to fixed point so I can more easily think about fractions. Fixed point is a scheme for representing fractions in a C integer format. If you don't like thinking in fixed point, don't use it. But I'll talk more about that over the period of this lab. So you're going to hook up one of these guys, and I gave you a pin out here for everything that needs to be connected, partly because I wanted to make sure it actually worked. Because you're going to use both SPI channels. One SPI channel is going to run the TFT display. The other SPI channel is going to run the DAC. They're completely independent. You can run them at the same time. You do have to worry a little bit about multiple use on these pins that I think some people have already run into. These pins are highly multiplexed, and some of the defaults are obscure. You need to config JTAG to off and debug to off in the config code. I believe that my code does default to JTAG off. I'm not sure it defaults to debug off. You may have to add that to the config.h. And my guess is there's going to be probably one big main thread. There's probably going to be some secondary threads, but the main thread is going to be a keypad thread. You're going to have to scan the keypad, and I'll say in a minute what I mean by that. We're going to have to run a debounce state machine to make sure that a key press is a valid key press and happens exactly once for every human initiated press. What? What does that mean? Well, it turns out that even very good switches bounce. These are not very good switches. These are membrane switches. So you would expect when the human presses, this is the waveform you'd expect. This is time, this is V at the switch, this is the press. And what you actually get is something that looks like this with a time constant of perhaps, a characteristic time of perhaps 5 milliseconds or 10 milliseconds. The button bounces. CMOS threshold is here. How many times did you push the button? 1, 2, 3, 4 times, says the computer. Even though the human, who's thinking on a time scale that looks like this, says I pushed it once. Therefore, you have to run a state machine that says, did you push it? Did you really push it? Are you really sure? Are you sure you did you release it? Are you sure you released it? And we'll talk about how to do that too. So it's gonna debounce the state, debounce the keyboard. It's going to have to build a digit buffer for memory of what's been entered, and of course it's going to have to trigger speech production. It's going to have to handle erase start commands, and this whole thing is going to execute about every 30 milliseconds or so, because you want it to be slowed down to a human speed. What's the bandwidth of your index finger? Anybody ever measure that? If you speed up your index finger, the amplitude drops. How fast is your index finger? You want to guess? I didn't say middle finger. Don't laugh. How fast is your index finger? It's probably about 5 hertz, more or less. You might be able to go faster. I don't think any of you can go 10 hertz with your index finger. So 100 milliseconds is enough. Is enough resolution. You want a little bit better resolution than that. But certainly you don't have to have microsecond resolution like the CPU can do. You want tens of milliseconds of resolution, which means you're going to run the state machine about 30 millisecond rate. Now that being said, there's probably somebody in here who is much faster. If you want to see an amazing video, go look up World Champion Quick Draw. The World Quick Draw Champion. There's this lunatic who can take, and I say lunatic because it's really easy to shoot your foot off doing this. He takes a gun, he pulls it out of the holster, he fires on target and puts it back in the holster in 100 milliseconds. It is inhumanly fast. I have no idea how he does it. It's so fast, you cannot resolve it in standard video, what he's doing. It's only 3 frames. It's crazy, but you have to see it to believe it. No, you can do that in your own time. Oh, look up World Champion Quick Draw. And I think he's using a 357 because it's a huge gun. Because he's lunatic. It's really easy to shoot your foot off. But most normal people would have a reaction time for a maximum repeat time on a button of no more than 5 a second or so. You might be able to get to 10 per second, but I don't think you're going to get any faster than that. So that's enough resolution. You want enough, but not too much. Any questions? Okay. So, keypad. The keypads we're using are laid out as a grid of 3x4 wires with a switch at each intersection, which is what you push. So what we need is a way of determining that this intersection, for instance, has been pushed and no others have been pushed at the same time. So we want to be able to isolate single intersections. The layout is going to be standard keyboard 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, and what is it? Star. I think these are somewhat arbitrary, star hash. And the way I decided to implement this, it's not unique, there's other ways to do it, but the way I decided to implement this was to wire the 3 lines to pull down resistors on the order of 10K or so, and then take these 3 lines off to input pins. Then sequentially drive each of the rows high for 1 clock pulse. Read which of these port pins gets pulled high, and that will give an intersection. So we're going to sequentially put a pulse here, then a pulse here, then a pulse here, then a pulse here. We're going to drive these all off of 1 port so we can manipulate them all simultaneously. And without fail, you must put resistors here. Typically 330 ohms, more or less, resistors. And why is that? These are all going to be set to outputs. These are all going to be set to inputs. Why are these absolutely necessary in this case? This is not optional, it's necessary. I heard the magic word short. Yes. So let's say that the silly human pushes these 2 buttons at the same time on 2 different rows, and there's no resistors here. This port pin is high, this port pin is low because this is a sequential scan. That means you have a high output hooked to a low output, both of which are voltage sources. One of the 2 transistors is going to win and blow the other one out. Probably the one that is low will blow out the one that's high, because what were the Thevenin impedances of the 2? Which one was the lower impedance? Which one was the lower impedance? You got to look it up? Really? Remember? Anybody remember? Anyways, go look it up. So the 330s here are not optional. However, if you want to, you can turn on internal pull downs, so you do not actually have to have physical resistors on the board along with the integrated circuit. You can turn on the internal pull downs, but you must either have external pull downs or turn on the internal pull downs, because a wire which is unconnected, an input which is unconnected, has an undefined voltage. And will read an arbitrary value depending on where your hand is relative to the keypad. So the scanning process then is going to be to put a pulse on here, read these 3 bits, put a pulse on here, read the same 3 bits, put a pulse on here, do it again, and see if any of the bits are high. And we have to have a way of detecting to make sure that the human has not pushed 2 buttons. That's an invalid. That's an invalid combination. So we need to be able to detect multiple pushes, and we need to be able to detect no push as well as a valid push. So what I did was and I want to make sure that what I ran on the board agrees with the code. I mapped these to A0, A1, A2, and A3 digital outs. And I mapped the 3 bits here to B7, B8, and B9. So that if I were to detect that a button was pushed, let's say that I detect that the 0 button is pushed, that's that button right there. If I detect that the 0 button is pushed because the middle pin, which is B8, recognized that A4 was high, we could uniquely identify that pin as, well, let's see, what is B8? B8 has a value of 0x100, right? That's B8. If B8 is the only one pressed. And A4 would have a value of 0x008. 1, 2, 4, 8. Yeah, 8. So if we OR these together, then we get 108 as being the unique code for one button pushed for the 0 key. Right? So when we detect that one of these is non-zero, that one of these rows is non-zero, one of the columns, when we detect that one of these 3 bits is non-zero, we OR together the value of the bit pattern in B register with the value of the bit pattern in the first 4 bits of the A register, output register, and we have the scan code for the number. So what's the scan code for 1? Scan code for 1. Where is 1? 1 is here, right? So when this button is pushed and we're scanning down the code, this wire, the B7 wire, is going to go high when A0 is high. So B7 has the value of 0x080, and A1 is going to be 0x001. We OR those together and we get 81.
Does that say A4?
That says A4, sorry, yes. It should say A3. Thank you. A3, sorry. Thank you. What else? So you can build a table now that will represent all 12 scan codes. If you search that table for the value at a given press, then the index of that table will give you which button was pushed. So, how do we, I'm going to go through the code. Not today, though, because we're too close to the end. I'm going to go through the scan code. But let's just do one last thing and say, how does this reject errors? We're going to have a list now of 12 values of the possible 512 8-bit, 9-bit numbers, we're going to have just 12 scan codes representing every possible valid press. How can we indicate an invalid press? Well, there's two cases. One is your finger bridges these two buttons and these are both pushed. That'll make an invalid code because the low bit will not be one of 1, 2, 4, or 8. It'll be some other number. Sorry, check. Yeah, no, it won't be one of sorry, it won't be one of 2 to the 7th, 2 to the 8th, or 2 to the 9th. It'll be some other number. How do we discriminate these two buttons being pushed? This is actually more problematical. At any given time, one of these is high and one is low. We push two buttons. What's the value of the voltage right here? The voltage divider between VDD and VSS, right? Because if this is connected high, this one must be low. That means this has got to be VDD over 2. Is that above or below the CMOS threshold? Come on, folks. What is the CMOS threshold? It's about VDD over 2, right? It's a very CMOS threshold is a very sharp threshold at about VDD over 2. Therefore, this is indeterminate. You don't know how it's going to read, how the port's going to read it. It's either going to read it as a very weak 1 or a very strong 0. So it may or may not reject. It may or may not reject that particular error condition without further processing. My guess is there's another part of the resistive divider, which is this 10K resistor, which is pulling the voltage down, as well as this resistor, which is also pulling it down. So that the voltage here is going to be just slightly, about 1% lower than VDD over 2. So it'll most likely read as a 0, and therefore reject that error. That says you don't want to make these resistors too big, because you're depending upon them to bias the system towards no response. But you don't want to make them too small, you draw too much current.
I was wondering, can you just change the other pins to high impedance?
So you could you, for instance, just float the other inputs? Sure. Yes. You could do that. You could dynamically make one an output and float the other ones. If you do that, put the 300 ohm resistors in anyway in case you mess up the code. Because otherwise you'll blow it. You'll blow the port. But yes, you could do that, and that simplifies it somewhat. That makes the error checking vertically very robust. Actually, does it. If you float one of these, if you float all three and leave this one connected, and you press these two buttons, that will not detect a fault. All it will do is say you pressed button 1. So it won't detect the fault. Whereas if you leave them all connected, and you have enough current flow through here, you'll get a 0 and it won't respond because you'll have a fault condition. You'll have 2 buttons pushed at the same time. So it might actually be a little better to have them driven all as outputs.
But you can just scan line 2 to see.
So then you have to do a special case. Then you have to see if there's 2 valid codes at the same time. That's right. So it makes the table lookup a little more complicated. Because now you have to do a table lookup, and you have to keep a memory of whether you've seen a valid code before or not, and if so, reject it. Yes, you could do it that way too. Read up on Lab 2. We'll talk more about it next time.